Welcome back. We're looking at solving a linear system of equation in 3 variables analytically. And the first example to look at is sometimes you have the case of where each equation is missing a variable. So we do have a procedure that you may have seen in previous classes, but I'd like to go over it again because we don't always have the same opportunities to practice. So starting off, what we're trying to look at in this first example is trying to figure out if we can pair up 2 equations so that we can eliminate one of the variables. So it doesn't matter how you start. Sometimes it's the first variable that you see that might be easily eliminated for yourself, or sometimes we just look at them in terms of they're already stacked up on top of each other and such. So first thing I'd like to do, just so that you know what equations I'm referring to, I like to label them, and I'll go from this side. Equation 1, equation 2, equation 3. And remember, when you label them with numbers, try not to get those numbers mixed up with the numbers that are already in your equation. So that's why I'm using green. And then what we want to do is we want to choose any of the 2 equations to eliminate one of the variables. So it's completely up to you whether you want to choose maybe 1 and 2 and eliminate the z's, or maybe you wanted to start with equations 2 and 3 and eliminate the x's. You could also go with 1 and 3 and eliminate the y's. So it's just the first one that you take to. So I'm going to go with equation 2 and 3. So whenever I'm showing the work for this, just to make sure that I don't skip any steps, I'll write them off to the side. So I have 4x plus 3z equals negative 12, and x plus 2y equals negative 1. The first thing I'm going to do is make a decision as to what variable I'm looking to eliminate. So I usually write a little note to myself, like, who am I eliminating? In my case, I'm eliminating x. That way I don't get confused later. So if I were to eliminate x, I need to figure out a number that both of the coefficients go into. So right now I have a coefficient of 1 in the equation number 3. And if I am trying to find a number that 1 and 4 both go into, I think the nicest number would be 4. So the top equation 2, number 2, already has a 4 as a coefficient. So I would want to multiply the bottom equation by a negative 4, because the whole goal is for the variables to neutralize out or cancel out. So you could always double check when you're done. Notice the top equation. I'm going to work horizontally. That way my eyes don't skip over any signs. Makes it a little bit more clearer. So when I multiply negative 4 to both sides of the equation, in equation number 3, I have negative 4x, and I'm going to actually color code that a little bit. So negative 4x minus 8y equals positive 4. So now if you add the equations vertically, the x terms will neutralize out, because 4x minus 4x is 0. Now, the interesting part about this type of system is that the 3z and the 8y are not like terms, so they cannot be combined. So usually what we do is we rewrite this negative 8y plus 3z equals, and I believe we're going to be looking at negative 8. So it's a 12 minus 4. I should double check. Sometimes the minor mistakes in these types of equations get us more than the actual process. So I always encourage you double check on your calculator for any of these minor computations. So what we have here is a new equation, and we may use this right away, or we may save it for later. But a lot of times you will see us refer to it as maybe the 4th equation. See how I label my equations differently? I use a circled number or a different color to help me out. Now, this type of system that we have is kind of non-standard because there are variables missing in each of the equations. At this stage, the way I would approach it is I would look to see if I could match up an equation from my original system to my equation 4. So I'd be looking for, do I have an equation that has both y and z in it? And if I'm looking at it, I do. I do have equation number 1. So what I'd like to do for myself is pair up these two equations. So I'll do this off to the side. I have equation 4, negative 8y plus 3z equals negative 8. That's equation 4. And then also equation 1. That's 7y minus 4z equals 7. So now what we can do is we could say, well, we're either going to eliminate the y's, or we notice that z is also located in the equations as well. So you make your decision. I'll just kind of do what comes first to me. I'm going to eliminate y this time. And if I eliminate y, I have to find a number that both 8 and 7 go into. And so with a little bit of number crunching, 8 and 7 both go into, I believe it's 56. So it gets a little bit high, but we have a calculator to help us out. So remember the goal is to get the coefficients to be positive 56 and negative 56. So it looks like the top equation, we already have a negative number. So you're going to multiply that by positive 7. That will give us negative 56y plus 21z equals negative 56. And now the bottom equation, it's got a positive 7. So if we multiply that by positive 8 on both sides, we will get a positive 56y minus 32z equals positive 56. We got lucky. It looks like the right-hand side of the equations also cancels out. So if we add vertically, we will notice that the y terms neutralize. And now we're left with 21 plus negative 32. So that's going to give us negative 11 z. And also, this doesn't always happen, but the 56 did neutralize as well. We do have ourselves a 0. So with this particular system, what we want to do is now we want to tie up all the loose ends. Now that we have one equation in one variable, if you want to divide both sides by negative 11, we can end up getting our z value. Z is going to equal 0. And what you can do is plug the z equals 0 back into one of the original systems of equations from when you eliminated y. So maybe I'll take this original equation before I multiplied it by 8. Kind of pull this over here for you all. Sometimes this needs a little bit more paper than what I've allowed. There we go. So we have z equals 0. If I'm going to plug this into 7y minus 4z equals 7, 7y minus 4 times 0 equals 7. So 7y equals 7. Divide both sides by 7. And you get y equals 1. So now you have a z value and a y value. And what you can do is take these z value and y value and plug it back into one of the original equations or any of the original equations. So you're able to get the x value. So it won't matter which one because we have a lot of different options. So we can go and say, well, I can either choose the top one again if I'd like to, but I have y and z already. I need to find something with an x. So maybe I'll choose this item number 3. And if I want to plug those in, I'm going to move sideways just to kind of show you. I'm looking at z and y. We're going to plug this into x plus 2y equals -1. And if we do that, what do we get? X is X. Y is already +1. So we end up solving X plus 2 equals -1. If we subtract 2 from both sides, we're going to get X equals -3. So now we have the common point that all equations are sharing. Usually you'll probably see this in the back of your textbook or your answers. It's okay if you want to circle X equals -3, Y equals 1, Z equals 0, but usually we'll have an ordered triple. Or ordered triplet, because sometimes it's different than the ordered pair. So usually you're always writing them in this format. So our final solution, usually you'll see this, the X term comes first, the Y second, and the Z last. So you'll usually see this as your final answer, -3, 1, and 0. So those take quite a bit of practice. They're not so standard because you usually have to choose 2 equations, eliminate a variable, and then pair up your new equation with one of the original equations. And then you'll end up solving a system of 2 equations, which then leads you to find the rest of the solutions. I'd like to take you on a journey to approach example 2, where we have equations where all of the variables are involved. So this ends up being a little more fun if we have a plan. So remember, if you don't have a set plan, you could be running yourself in a lot of different circles. So I like to give you something to help. The first thing you'll want to make sure of is, are your equations all in standard form? X's are on the left, so are Y's, so are Z's, and numbers are on the right. Looks like all the X's, Y's, and Z's are in order too, so that's nice. The next thing is to understand if we're labeling our equations. Usually I label them 1, 2, 3, just so I can keep track as I go along. What I'll be interested in doing here is choosing any 2 equations and eliminating one of the variables. So we have lots of options. What I'm looking at is maybe the fastest one for me to eliminate, and I don't know if you see it, but I already see equations where I don't have to do much to them. The X's will drop out. So I'm going to choose 2 and 3. And I'm really careful with trying to modify any sort of writing around my original system. Sometimes that messes me up. I miss a number or I accidentally skip over. So I'm taking my time to rewrite my equations that I've chosen. X plus 2y plus 4z equals 0. I'm also noting to myself that I'm eliminating the X terms. That's going to be important later because we want to make sure we do the same thing. We are very lucky in this sense. We don't have to modify the equations at all. So you'll notice right away when you add them vertically, the X is neutralized. So we have 1y plus 2y, which is 3y. 2z plus 4z is 6z, and 3 plus 0 is 3. So this is going to leave us with a 4th equation. And we're going to save this for a second. We're going to save this off to the side. Now, there may be other cases where it might be easier to eliminate a y or eliminate a z. But if you made the decision to eliminate the x at first, you need to choose another pair of equations that also eliminate x. Otherwise, we're going to run ourselves in a circle. So we already chose equation 2 and 3. Now maybe we can choose 1 and 3 or 1 and 2. I might do 1 and 2 because I already see that these signs are already opposites in a sense. So I'm going to choose another combo. And again, I'm going to remind myself that I'm eliminating x on another pair. Okay, so I'm choosing, this time it's 1 and 2. And so I don't get confused, I write everything off to the side. I don't really mess with my original system. Otherwise, it gets a little hard to read and we're more likely to make mistakes. So now remembering for ourselves, if we are eliminating x, our goal would be to find opposite coefficients. So in our case right now, we have a 2 and a negative 1. So our goal would be to find a positive 2 and a negative 2 to be as the coefficients. So equation number 1 is good to go. We can write that over again. It already has a positive 2x plus 2y plus z equals 1. And equation number 2, that would be, we would have to multiply that by 2 on both sides so that we get that negative 2x that we needed. So I have negative 2x plus 2y plus 4z equals 6. Notice that we're distributing. That's kind of something I know sometimes when we're looking from left to right, causes some issues. So now we're going to add vertically. And what should happen is our x terms should cancel out. And they do. So we have 4y plus 5z equals 7. And notice the reason why we had to choose x in both cases is because now you have two equations in the same two variables, both y and z. So what we would do at this point is now we're going to pair these two equations up. The 3y plus 6z, so that's equation number 4. y plus 6z equals 3, and equation number 5. 4y plus 5z equals 7. And you can decide, do you want to eliminate the z or do you want to eliminate the y? Completely up to you. I'm going to go with eliminating the y's just because they're closer. So I'm making myself a note. Right now I'm noticing that the coefficients of my y's are 3 and 4. So I need to find a number that both 3 and 4 go into. And the smallest number is 12. So my goal is to get a positive 12 and a negative 12. See how I'm, all this I'm thinking in my head, but I do write myself notes so I don't lose track. So what I'd have to do, I'm going to multiply the top equation by a positive 4. So that's going to leave me with 12y plus 24z equals 12. The bottom equation, because I need a negative, I'm going to multiply this by negative 3 on both sides. So this will leave me with negative 12y minus 15z equals negative 21. So now I'm going to add vertically. Notice that the 12y's eliminate just like we needed to. And now we're looking at 24 plus a negative 15. So that's giving us a 9z. And then 12 plus a negative 21 is giving us a negative 9. And so this is nice because at this point we can solve for z by dividing by 9 on both sides. So we do get z equals negative 1. Just circle that. And then now it's kind of like a matter of just resubstituting everything we know. If we know that z is negative 1, it's really nice to tie up this system and plug z into one of the original equations. I could do that over here, I suppose, or I could do it right next to myself. I have a little more room on this one. So I'm choosing 4y plus 5z equals 7. So 4y plus 5 times negative 1. That's a lot of algebra, but you guys are pretty good at this by now. So what do we get? 4y minus 5 equals 7. We're going to add 5 to both sides. We'll get 4y equals 12. And solving for y, we divide both sides by 4. We will get y equals 3. So we have another solution for ourselves. Now, if you have z and you have y, you can go back to your original equations and choose any of the 3 and find your x. So I'll kind of do that. I'll go over here, see if I can. Let me write down what I just found, just so that we are clear. We got z equals -1, y equals 3. So do that with you. And I'll double check to make sure, because that's kind of our biggest mistake if we miss a sign when we're recopying things. So I'm going to take those two values. I'm going to pick any of the original equations. Might as well pick the one I see first. I just chose the bottom one. And so I'm going to plug this in. So x plus 2y plus 4z equals 0. I don't know who x is, but I do know that y is 3. And z is -1. We'll plug that in. And that leaves us with x plus 6 minus 4 equals 0. Do a little bit of combining the like terms. We have x plus 2 equals 0. Subtracting 2 from both sides. To solve for x, we're going to get x equals -2. So now we have all 3 variables. It's fine if we circled them throughout our work, but usually when we enter them in, we're entering them as an ordered triple. So the solution would be always x, which is -2, y, which is 3, and z is -1. So we have our final solution. Nice and compact there. So I cannot emphasize enough just trying your best to be organized with your work. Sometimes if you take shortcuts when you're solving systems of equations analytically, we miss one thing and it throws the entire system off. So I want you to be extremely careful. I tried to model it the best way I can with color coding and such, just so that you can stay organized as well. So I hope this helps. I'll see you in the next example.